Hey everyone, so in this video we're going to be talking about what are called sampling distributions. So just a refresher on some terminology, parameters are fixed values that describe a population, like the population mean, mu, or the population variance, sigma squared. And statistics are calculated values that describe a sample, like the sample mean x bar or the sample variance s squared. Now, recall that the value of statistics, like x bar, can vary, while the values of parameters don't vary, they're fixed. And the reason x bar will vary is because each time we take a different sample, the sample mean is going to be different. And since the sample mean is a function of random variables, the sample mean itself is a random variable. And since it's a random variable, we're going to use a capital X bar to denote this. And just like any other random variable, X bar has its own distribution. And we call this the sampling distribution of the sample mean. So let's talk about the sampling distribution of the sample mean. So remember that we can calculate the expectation and the variance of random variables. So remember that if x follows a binomial distribution with parameters n and p, then the expectation of x is n times p, and the variance of x is n times p times 1 minus p. And remember also that if x follows a normal distribution with parameters mu and sigma squared, then the expectation of x is mu, and the variance of x is sigma squared. But what happens with our sample mean, x? So if x has a mean of mu and a variance of sigma squared, what will we expect to happen to the mean and the variance of x bar from a sample of size n? And on the surface, this isn't exactly the easiest question to answer. So in this case, I think it's probably better to look at an example first. So suppose we draw a sample of size 2 from a population with the following distribution, and here is a PMF. So there's a 0.5 probability that x will be equal to 4, there's a 0.2 probability that x will be equal to 6, and there's a 0.3 probability that x will be equal to 9. So we can calculate the expectation and the variance of this. So remember, to calculate the expectation, we just added up each of the x values times their probability. So this is going to be 4 times 0.5 plus 6 times 0.2 plus 9 times 0.3. And when we do that, we end up getting 5.9. So that is the expected value of this random variable. And the variance, remember, this is going to be the expectation of x squared minus the expectation of x squared. So this is going to be the sum of each of the x values squared times their probabilities minus mu squared. So for this first piece, you'll just have to trust me that it's 39.5. And then this second piece, we already figured out that the mean, or the expectation, was 5.9, and we're just going to be squaring that. And if you do this math here, then you will end up with 4.69. So now what we have to do is we have to find the distribution of x bar. So that was the distribution of x and the expectation of x and the variance of x. But now we're interested in x bar. And remember, we're taking a sample of size 2. So we're drawing from x twice. We're adding up those two observations and we're dividing by 2. So there are 9 different outcomes of what could happen. So remember, we could get a 4 or a 6 or a 9 each time we draw from x. And we're going to be drawing from x twice. So we could get 4, 4, we could get 4, 6, we could get 9, 4. There are 9 different possible outcomes of what we could get here. And if we list out each of these outcomes, we'll end up with something like this. Our first observation could be 4, and then our second observation could be 4, or it could be 4 and 6, or 4 and 9. These are the 9 different possibilities of what could happen. And we're interested in the distribution of x bar. So if we took each of these combinations here and averaged out these samples of size 2, then what we would get is this column right here, which is x bar. So for example, if we get 4 and 4, then our average is going to be 4. If we get 4 and 6, then our average is going to be 5. If we get 6 and 9, then our average is going to be 7.5. And we can do that for each of these possible outcomes. So now the only other thing we have left to do is we have to take into consideration the probability of each of those outcomes happening. Because, for example, 4 has a higher probability of being drawn than 6 or 9. So it's more likely to get, for example, 4 and then 4 than it is for us to get 6 and 6, because it's more likely for us to draw a 4. But we know the probabilities of getting each of those combinations because they're independent draws, so that means we can just multiply their probabilities. So the probability of getting 2 4s, for example, would be 0.5 times 0.5. So in that case, it would be 0.25. So that's why we have that listed right here. Similarly, with 4 and 6, remember the probability of a 4 was 0.5 and the probability of a 6 was 0.2. So if we multiply that together, then we'll come up with 0.1. And we can do that with each of these possible outcomes. And we'll end up with this table right here. Now, the last thing we have to do is notice we have some duplicates here. So we have 2 5s here, we have 2 7.5s here, and we have 2 6.5s. And since there are multiple ways to get those, we could just add up their probabilities. So what we can do, for example, for 5, the probability of getting a sample mean of 5 is zero point 0.1 plus zero point 0.1. So the probability of getting a sample mean of 5 is going to be 0.2. So now we can clean up this table by grouping those together. So when we group those together, we get something like this. So now this looks a little bit different compared to our original PMF of X, because now we're taking into consideration each of the possible sample means. But again, since X bar is a random variable here, we can calculate its expectation and its variance. So let's do that. So the expectation of X bar is going to be the sum of each of the values of X bar that are possible times their corresponding probabilities. So that's just going to be 4 times 0.25 plus 5 times 0.2 all the way down the line. And when we do that, we end up with this. And if we do all this arithmetic here, then we come up with 5.9. And that should look familiar to you because this was the same as the expectation of X. This was the mean of X. So in general, this is always the case. The mean of X bar is just going to be the same as the mean of X. And now the variance is going to be the sum of each of the possible values of X bar squared times their probabilities minus the mean of X bar squared. And when we do this, this is going to be 4 squared times 0.25 plus 5 squared times 0.2 all the way down the line. So that's what this piece is right here. And then again, we're going to be subtracting off the mean of x bar, which we just determined was 5.9, and we're going to be squaring it. So this is going to be 37.155 minus 34.81. So this ends up being 2.345 for our variance. And if we go back and look at what our variance of x was, we will find that our variance of x was 4.69, which is higher than our variance of x bar. And in fact, this is exactly half of the variance of x. So for this example, when we manually calculated the mean and the variance of x bar, we found that the mean or the expectation of x bar was the same thing as the expectation of x. And the variance of x bar was the variance of x divided by 2. So in general, if x has a mean of mu and a variance of sigma squared, then the expectation of x bar is also going to be mu, and the variance of x bar is going to be sigma squared over n. And this lines up with the example we just did. The means were the same for these two, and then the variance of x bar in our example was the variance of x divided by 2, since our sample size was 2. So what about the shape of the distribution of x bar? So if x bar follows a normal distribution with a mean of mu and a variance of sigma squared, then x bar will also have a normal distribution, and it will have a mean of mu and a variance of sigma squared over n. So in other words, if x is normal, then x bar is also going to be normal, and that's going to be exact. But what happens if x is not normally distributed? So this is where we get into the central limit theorem, and this is probably the most profound theorem in all of statistics, and a lot of statistical theory is based off of this one theorem. So it's actually very important, and it's actually pretty cool. So for a random sample, the central limit theorem, or we call it the CLT, states that as the sample size gets larger, the sampling distribution of the sample mean is going to be approximately normal, regardless of the shape of the underlying distribution. And the general rule of thumb is that we can apply the central limit theorem when n is greater than or equal to 30. That's when n is large enough to say that this distribution is going to be approximately normal. And as I said, this is arguably the most important theorem in all of statistics. Well, let's look at an example. So suppose the distribution of male heights is normally distributed with a mean of 70 inches and a standard deviation of 3 inches. So what's the probability that one randomly selected male is taller than 74 inches? And we've actually done this problem before. This has nothing to do with the sampling distribution of the sample mean, but we're going somewhere with this. So the probability that x is greater than 74, so remember our first step here is we have to standardize x. So we have to subtract the mean and divide by the standard deviation. And to keep this inequality valid, we have to do the same thing on the other side. So we're going to subtract 70, which was the mean, and then divide by 3, which was the standard deviation. And then notice that this is going to be z because we standardized it. And then when we do the math over here, we come up with 1.33. And just like before, when we did the examples in the previous video, we're going to flip this inequality around, and the way we do that is by subtracting from 1. And then we can look this quantity up on the table, and if we do, we'll get 0.9082, and when we subtract that from 1, we'll get 0.0918. So now what if we were asked about the probability that 4 randomly selected males have a mean height taller than 74 inches? So now what we're looking for is the probability that X bar is greater than 74. So remember, if X is normally distributed with mean mu and variance sigma squared, then X bar is going to be normally distributed with mean mu and variance sigma squared over n. So for this problem, since we're going to have to end up standardizing this at some point, it's going to be helpful to find the standard deviation of X bar instead of the variance. And remember, to find this standard deviation, all we have to do is take the square root of the variance. So this was the variance of X bar, and if we take the square root of that, we'll end up with sigma over the square root of n. And that'll be our standard deviation of X bar. So now we have all the information we need to calculate this probability. Remember, the mean of X bar is going to be the same thing as the mean of X, and that was 70. And then the standard deviation of X bar, we just found out that that was sigma over the square root of n. So that's going to be 3 over the square root of 4. So that's 3 halves. So that's 1.5. So now we have the correct mean and the correct standard deviation, so we can carry out the typical calculation that we've done in the past. So we take this X bar and we can standardize it by subtracting its mean and dividing by its standard deviation. So this is going to be 74 minus 70 divided by 1.5, because the mean of X bar was 70 and the standard deviation of X bar was 1.5. So now we just need to calculate the probability that Z is greater than 2.67. And just like before, we flip this inequality by subtracting it from 1, and then we can calculate this probability right here by looking it up in the table. And when we do, we get 0.9962. And when we subtract that from 1, we end up with 0.0038. So it's very unlikely that we select 4 males who have a mean height of taller than 74 inches. So now what's the probability that 36 randomly selected males have a mean height taller than 74 inches? So again, we're going to do the same thing. We already know what the mean is because the mean of X was 70. And then the standard deviation of X bar now is going to change because our sample size changed. So this is going to be 3 over the square root of 36. So now our standard deviation is going to be 0.5. And when we go about our normal probability calculations, we'll eventually need to know what the probability of Z being greater than 8 is. And think about what it means for a Z value to be 8. That means something is 8 standard deviations above the mean. And remember, if you remember what the normal curve looked like, it started to flatten out and get pretty thin around like the 3.5 mark. So for something to be 8 standard deviations above the mean, it's so incredibly unlikely that the probability of Z being less than 8 is pretty much 1. So we could say this is approximately equal to 1 minus 1, so that's going to be approximately 0. So in other words, it's almost impossible to select a random sample of 36 males that have an average height taller than 74 inches. So here's another example. So let's say the salaries at a large corporation have a mean of $50,000 and a standard deviation of $21,000. So what's the probability that 15 randomly selected employees will have a mean salary less than $52,000? Now, the problem with this is that it might be tempting to carry out a normal probability calculation as usual, but we don't know anything about the distribution of the salaries. So since we don't know this is a normal distribution, we can't carry out this calculation. And since the sample size is less than 30, we can't even apply the central limit theorem here. So this actually means that we don't have enough information to answer this question. So now what if we asked about the probability that 49 randomly selected employees will have a mean salary less than $52,000? So now we're dealing with a mean from a random sample of size 49, which is greater than or equal to 30. So now we can apply the central limit theorem here and declare that the distribution of X bar is going to be approximately normal. So that means we're allowed to carry out our normal calculations using the normal distribution. So just like with the heights example, we'll have the mean of X bar equal to mu, which is 50 for 50,000, and the standard deviation of X bar is going to be sigma over the square root of n. And remember, the standard deviation of the salaries was 21, and our sample size is 49. So this is going to be 21 over 7, or 3. And so that means when we carry out our normal calculations here, we can standardize X bar by subtracting its mean and dividing by its standard deviation. And then on this side, we're going to have 52 minus 50 divided by 3 because our mean was 50 and our standard deviation was 3. And in this case, we're going to get the probability that z is less than 0.67, which is 0.7486. So this means that the probability that 49 randomly selected employees will have a mean salary less than $52,000 is 0.7486. So anyway, that's the end of this video. I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.